So in section 7.2, we're going to talk about integrating when a U sub or none of the techniques we've talked about so far will work. And the issue that's going to become that we're going to have to figure out is how do we integrate when there's a product or a composition in your integral and a U sub does not work. As you know, there's no product rule for integration. So one method we can try is what's called integration by parts. So the formula integration by parts starts with a product rule. So notice if I take the derivative of a product, u times v, I have u prime v plus uv prime. Next, what I'm going to do with this equation is I'm going to integrate both sides. So I integrate each term on the right-hand side. Next, I'm just simply going to simplify. So again, I know that the integral of the derivative uv is just going to give me a uv. Then I'm going to solve for my integral of u times v prime. And then I'm just going to rewrite this statement that I have. I'm going to let v prime be equal to dv. I'm going to let u prime be equal to du. And this is where my integration by parts formula is going to come from. So the strategy that I need to do is I'm going to have to rewrite my integral that was a product in terms of u and dv. And when I integrate u times dv, it's going to be equal to u times v minus the integral of v times du. So for example, let's suppose I have this integral x times cosine x. Notice I have a product. I have x being multiplied by cosine x. A u sub is not going to work. So what we're going to have to do when you do integration by parts is you have to make a choice. You have to let one of the functions be equal to u and the other one be in terms of dv. So let's suppose I let u be equal to x and dv be equal to cosine x dx. So if I let u be equal to x, first thing I need to do is I want to find my du. So the derivative of x is just going to be a 1 times dx. Then I have my dv is equal to cosine x dx. So now what I want to do is integrate cosine x. And I know the integral of cosine x is just going to be a sine x. So then what I want to do is I'm going to integrate using my parts. So the integral of u times dv is going to be equal to u times v minus your integral v times du. So since u is my x, dv is my sine x, then the integral of x times, dv is cosine x. That's going to be equal to u times v, which is x times sine x, minus your integral of v times du, which I found to be dx. So the only thing left to do then is I should now have an integral I can integrate. So then I have x times sine x minus, and I know the integral of sine x is a negative cosine x, that's going to become a plus cosine x. And again, I'm dealing with my indefinite integral, so don't forget to add your c. So the problem we run into, or the strategy we have to be able to do, is being able to select which function is going to be u and which function is going to be dv. And remember, we can always check our answers after you do parts by taking the derivative. So they're not going to tell you what u is going to be equal to and what dv is going to be equal to. We're going to have to figure that out. So what we want to do is you want to make sure that u has the derivative that becomes simpler. And dv is easy to integrate. To help us find v. So here's a statement light that may help you decide what u should be equal to. So again, this is helping us decide what u should be equal to. So the L in light stands for logarithms. So if one of your functions in the integral is a logarithm, then let's let u be equal to that logarithmic function. Next is check for an inverse trig function. Next is an algebraic function. T stands for a trig function. E is for an exponential. And what we want to do is to let u be equal to the function whose category occurs earlier in the list. And dv will be the rest of the integral. This method doesn't work all the time, but it is a good way to get started. Sometimes you may have to switch it around, change what u was equal to and what dv was equal to. So here's an example. We have x times e to the x. Notice we have an algebraic function, we have an exponential function, and a u sub is not going to work. So using my phrase lie8, there is no logarithmic function, there is no inverse function. However, I do have an algebraic function of x. So I'm going to let u be equal to x. dv is going to be the rest of my integrand, that e to the x dx. So now what I'm going to do is I'm going to take the derivative of u, and the derivative of x is just going to leave me with a dx. When I integrate dv, that'll help me find v. And the integral of e to the x is just an e to the x. So now what I want to do is plug them into my parts formula, u times v minus my integral of v times du. So I have u times v, which is my x times e to the x, minus my integral of v, which is e to the x, times du, which is a dx. And when I integrate e to the x, that's just going to give me an e to the x plus c. So that's how the integration by parts works for that particular example. So let's take a look at b. We have x times the natural log of x. Notice I have an algebraic function multiplied by a logarithmic function. U sub's not going to work. So you're looking at the phrase lie8, notice the L stands for logarithm. I do have a logarithm function in here, so I'm going to let u be equal to the natural log of x. My dv is going to be the rest of the integrand, which is my x times dx. So now I'm going to take the derivative of u. So the derivative of u is going to be a 1 over x times dx. My v, when I integrate x, is going to give me an x squared over 2. So now I'm going to plug it into my parts formula, u times v minus the integral v du. So natural log of x times x squared over 2. There's my u times v, minus my integral of v, which is my x squared over 2, times du, which is my 1 over x dx. So when I clean up this integrand, I still have the natural log of x times x squared over 2. He just tags along to my final answer. I can pull out that constant of 1/2. X squared divided by an x is just going to leave me with an x times dx. So when I integrate x, I know that's going to be an x squared over 2. So I have minus 1/2 times x squared over 2 plus c. And I can clean this up to give me natural log of x times x squared over 2 minus 1/4 times x squared plus c. So that's your integral of x times natural. And like you said, if we took the derivative of this, we should get back to the x times natural log of x. So let's take a look at c. We have x times the sine of 3x. So when we take a look at the list, no logarithm function, no inverse trig, but I do have the algebraic function of x. So I'm going to let u be equal to x. My dv is going to be the rest of that integral, the sine of 3x dx. So when I take the derivative of u, that's going to leave me 1 times dx. Now be careful when you integrate dv. You're going to have to do a u sub. U is equal to 3x, du is equal to 3 dx. So I can pull out that 1/3 times your integral of sine of u du. So when I integrate, I know the integral of sine is going to be a negative cosine. That's going to be a negative 1/3 cosine of 3x. So now let me plug it into my parts formula, u times v minus your integral v du. So u times v, so x times negative 1/3, so that's where I'm going to get a negative x over 3 cosine of 3x. Minus your integral of v, which is that negative 1/3 that I'm going to pull out, so I'm just going to write this as a plus 1/3, cosine of 3x times my du, which is a dx. So now I'm going to have to do another u sub. I know u is going to be equal to 3x. My du will be a 3 dx. So when I rewrite this integral in terms of u and du, I'm going to have still that negative x over 3 cosine of 3x. This is going to turn into a plus 1/9 constant times my integral of cosine of u du. And I know when I integrate cosine, that's just going to give me a sine. So my final answer then is going to be a negative x over 3 cosine of 3x plus 1/9 times the sine. Again, I'm going to replace u with that 3x plus c. Now sometimes in your integral, if you take a look at D, it appears that you only have one function, integrating just natural log of x dx. You actually do have a product. You have natural log of x, which is being multiplied by dx. We don't have a ruler. We haven't talked about how to integrate natural log of x. So I can integrate natural log of x by using parts. So again, using light, I can let my natural log of x be equal to my u. So u is equal to the natural log of x. My dv is just going to be my dx, because I can integrate dx. So du is going to be 1 over x dx. When I integrate dx, v is just going to be equal to x. So I can plug it into my parts, u times v minus the integral of v times du. So I can take u times v, which is x times natural log of x, minus my integral of v, which is x, times my du, which is 1 over x dx. Again, I can multiply x times 1 over x, which is just going to have me integrate dx. So when I integrate dx, I know that's just going to be a minus x plus c. And those are some examples of using integration by parts.